Hi guys, we're now going to work on Euler's method for numerically solving differential equations. So this is used, we're going to essentially use the slope field idea, and we're going to find particular solutions for differential equations which you cannot solve by splitting the variables. That's the idea of doing this. So just to go back to slope fields for a second, let's just talk about how we could find different solutions. So we've got this graph, and we kind of did this one by eye. Now you could introduce an algorithm to find this graph essentially. So you could find any point on here by following the gradient at any particular point. Now we've only made gradients on the kind of integer points, 2, 4, 1, 4, and so on. So, but you could actually find that to a much finer detail. And that's essentially what we're going to be using. So for example, for this one, if we took this point, we know that 1, 0 is on our line, and this is our slope field. And they gave us the differential equation, which was in the question. Then what you could do is say, well, look, I'm going to get to my next point by just going 1 across and using this gradient, which maybe is 2, takes me up to here. Okay, so we're there. And then at this point, let's just see that point, maybe that's a gradient of 1, I don't know. At this point, that's a gradient of 1. So next, we're going to go across 1 and up 1, and there we go, that will be our new point. Okay, so we go up to there, and then we go 1 across again. You can see it's a gradient of 0, so I go 1 across. And maybe this is a gradient of -2, I'm not sure. So -2 would take us down here. Now you can see that this is kind of going too far this way. And that's because the curve is turning in this particular direction. But if we used much smaller gaps, say for example we used 0.1, then we would be much closer, still sort of an exaggeration, that we'd be much closer to the curve itself. And obviously if we used 0.01, we'd be even closer to the curve itself. Again, we'd go slightly off, but we would get a fairly good approximation if we could make those amounts smaller. So what I'm talking about is if we just get rid of all of this, what I'm saying is instead of going across 1 and up 2 here, we use that gradient of 2 and go across maybe 0.1 and up 0.2. And then we find the gradient at that point, and we do the same process again, okay, to follow around the curve. Right, that's the idea. And in the book, it seems pretty difficult because they give you, this is pretty difficult to read through. They give you this formula here, but that's it's actually fairly straightforward. It's just saying, let's add on to our previous height, whatever distance we're moving across, times by the gradient. So for example, let's just have a look at this one here. If we were at 0 as a height, what we would do if we had a height of 0.1, h being that difference in x. Okay, so h would be that small amount of x that you're adding on in this direction here. So we'd say, well, that times by the gradient would take us up here. So for example, if h is 0.1 in this case, and say for example our gradient is equal to 2, then we'd need to go up a height of 0.2. And if you have a look at that in here, that would be saying 0.1 times by 2 would give us a 0.2 that you'd need to add on to get to that next point, which would be 0.1 further along the x-axis. Now, the m is this thing here. This is your function. Now, they don't say f dash because they've defined the function here, the y dx, they've just called it a function of x and y. But we're often used to calling that f dash of x, but they've defined it as f of xy. It's just a function of x and y. Okay, so it's dependent on x and y, not just on x, which is what we're normally used to when we're not doing differential equations. Okay, hopefully that's all fairly clear. So let me take this again. Let's just take let's take a bit of this and just explain it through again. Okay, so yeah, they're saying here, consider this differential equation at the top. They're saying let xn minus 1, yn minus 1 be a point on the curve. So they're saying that's your start point. And what we're going to try and get to is the next point. So the next one. And if we do it once, we can do it again and again and again to get to each next one. And we'll have an iterative formula or a recursive formula, which will take us around to make the equation of our line. Okay, so this is our point here, xn minus 1, yn minus 1. That's the coordinate point here, x minus 1, yn minus 1. Okay, so to get to the next point, we need to take the previous one. So x. So they're saying to get the next x number. By the way, sorry, that's the first part. Missing that out actually. To get the first x number, we're saying the next x number. We're just adding on our change. Remember, h is like our change, our small change in x. If you want, you can call it an actual change, capital delta x. Okay, but a small change in x is going to take us to the next one. So say, for example, in this case, if xn minus 1 is equal to 1, say that's 1 on the axis here, to get to the next point, we would say, okay, well, let's add on to that the height. And the height might be, for example, we're going up in 0.1s. And that would give us the next point, give us xn, and that would give us, in this case, 1.1. That would be the next point that we're seeking a y value for. Okay, hopefully that's all clear. So that's the first formula. It's just saying what we're going up in. There's nothing difficult there. And the second formula, which we're generating here, is essentially saying, okay, well, to get yn, you need to take the previous height and add on the gradient. So that small change in x times by the gradient. Okay, so small change in x in this case is h, and that's times by the gradient at that particular point here. So it's not the same, it's not the gradient all the way through, but it's the point here. Okay, it's the gradient at that point. It's not actually the gradient at this point, but again, it's an approximation. Okay, so hopefully that's, I mean, you can obviously read that one through, take your time to read that one through, but then you're going to get this f of x n minus 1, and fit in y n minus 1. I'm just writing down this thing again. Hopefully that is clear. That is taking us up to the next point. Okay, so that's our iterative formula. Now let's look at one of the questions. And I'm going to do the questions in two ways. I'm going to do it on Excel, and then I'm going to do it on the calculator as well. So this is going to take a bit of time. Okay, now here we go. They're saying let's do this. Let's for example, in this case, here would be our approximations to the curve. They're just giving us an example that we're going to do many times. Okay, so let's look at an example. Okay, so example 25. So use Euler's method with step size 0.1, be a common step size to use. 0.01 would be even better. Okay, to approximate the solution to the initial value of this problem here. And they're giving us, in this case, a very simple formula for the derivative, which is based on both x and y. And they're saying that they're giving us a start condition. They're saying when x is 1, y is 1. They're basically saying we've got this coordinate point here. Normally, by the way, we use the notation f of 1 is equal to 1. But in this case, they're saying, well, they're saying y of x. Y is dependent on x. Okay, so that's the notation which they're using. To estimate this thing here. So we're going to need 10 steps to take us up in 0.1s along the x-axis to get to y2. Okay, let's see if there's a little graph of this one or not. No, there's not a graph, it's just a table. Okay, but actually your calculator does give you a table, but we'll deal with it with Excel to start off with. Okay, so I've started putting in my initial conditions here. Let's just zoom in a bit. And it's worth trying to create this yourself just to see how it all works. Try and make it at the same time as we're doing this. So 0, 1, 2, that's our n, if you like. this is going to be our first time we get to the next place, but this is going to be our start point. If you like, that's our n minus 1 when we were talking about the general situation. And this is going to be n, and this is going to be the next one, which would be n plus 1. Okay, but we can just call this our n in this case. It's just the step number. Okay, and this is going to be our x number, and this is going to be our y number. Okay, and we were told that when y was 1, x was 1, or when x was 1, y was 1. So there's the coordinate point which I've just put in, and I've just put in the first couple of steps. I can see that we're going up in 0.1, so I've just put in the first couple of x values there. Okay, so for y, we're going to need to build this formula, and the formula was the previous y number, so in this case that's in D2, plus the height, which was 0.1, because we're going up in 0.1. When I say height, it's the distance across, it's that small change in x. Now that's times by the gradient. Now the gradient function in this case was actually x times by y. So now I don't know what x and y is here and here because I'm looking for that y value here. So I'm going to use the previous one just as I'm using the previous one for y here as well. So I'm using the previous x and y values. Now this is my function. This is what I'm putting in here is my function of x and y. That's what I'm putting in. Okay, that's my derivative function that I'm trying to find. Now they told us it was x times by y, so I'm putting in here c2 times by d2. That was the previous derivative at the previous point, the gradient at the previous point 1, 1. Okay, so now I've got that. I can put that in, and I can copy that, and I can paste that, and there's my next value. Now, if I take all of these, and if I drag this one down here, this will give us our x values going up and approximations to our y values, which are probably going off the curve. But again, if we take smaller values for this, if we chose your small change in x to be 0.01, you'd be much closer to the curve. Now, we're asked to find out the value when x is equal to 2. So the value when x is equal to 2 is after our 10th step. So this is only our step number here. And that's now at 3.860. So that is our answer. This is our answer here. Okay, let's just check that in the book to see what they've done. There we go. And they just say, helpfully, use technology. Okay, well, we're going to use technology in a second other than Excel, but that's exactly what we've just done here. Now, have a look at this. They've just done this slightly differently here. And all they've done is factorized out the yn minus 1 from both of these expressions here. Okay, now remember again, this xn minus 1, yn minus 1 was the function for the derivative in this case. You might have to put in a more complicated function for that derivative. Okay. In fact, this is one which you could actually have split up, but we're doing this as an example, of course. Okay, so there we go. So they've factorized out this, and actually they use a factorized version of this when they do it on the GDC. Okay, now, if you have a look at the online version of the book, you can look through the GDC version of this. It's fairly straightforward, but I'll just talk it through a bit as well. I just did it earlier myself. I actually learned something here too. I've got it here actually, somewhere here. Okay, so this is the same question, I think. Just have a look down. Where are we? Here we go. It's this question here. Okay, so this was the example which we've just done. I've just done it on Excel. Now, this is pretty cool, to be honest. I didn't know about this, but you can open up a new graphs page. And when you do that, you just follow the instructions. By the way, this was, when I opened that link up, it took me to TI Inspire, but there's other calculator options which give you there as well. And if you've got a different calculator than the three which they give you, three options which they give you, then you're going to have to find it out on YouTube. Sorry about that. We obviously recommend this calculator, that's the one which we use. So, okay, so here we go. We're going to make this iterative formula essentially. Now, they can't put in y, x. It has to be done in terms of u, right? When you come up with these sequences, these iterative sequences, that's what we're about to create. So instead of f1 of x, you're going to put in u1 of n. Okay, now also we said that was our first term and our zero term, and in fact this is our first function. Okay, so there's potentially a little confusion here. Yeah, okay, this is our first function, and our first function is going to be essentially for x. Sorry, this is going to be for x. So we're going to put this thing in to start off with. If you have a look back at the book, sorry, this is taking a while. Okay, and so if you have a look back at the book, there is the function that we first need to put in. We need to say what's happening with x, and then we're going to relate it with a function with y there as well, and it will come up with a table for us. Okay, so let's go back again to here. So here we go. The function for x is going up in 0.1. So this is pretty straightforward to put in. You need to put in here the nth term is the previous term plus 0.1. Okay, and u1 is the formula. It's the way in which we call the function x. So because you can't put in x here, it will only give you choices of u1, u2, u3. Those are different functions which you put in, and we're putting in the function for x. Now the initial term for x is 1. So that's saying that's where we start with x. And we're going, the step is how many steps we've got. Now they're just going up to 99 here because they're just saying, well, we want to go up to 99. Okay, and that should do for your questions. So that's not saying that it's going to go up to x is 99. That's just saying we're going to have 99 of these little steps in a massive table, but perhaps we'll only need the 10th one. Okay, so we'll be able to see that in the table. Okay, so once you put that in, it will plot this graph for you when you press equals. And now we need to put in another one. And so when we put another one, we can press tab and you'll get another entry line. And by the way, if you use your cursor keys, you can go up and down to the previous one or the third one if you want to relate it to a third one. Okay, so to put in y, we're going to call it u2. And we're going to, again, relate n to n minus 1. So the next term to the previous term, current term to previous term. And in this case, they're putting in this function here from, let's show you here. They're putting in this function here. They're putting in a factorized version of this thing here. For myself, I would just put in this actually. I don't see why I wouldn't put in that, but they've factorized it and that's what they're putting in. Okay, so I'm going to that one instead. So they're putting that one in, the factorized version. Again, they're starting at 1 because we were told that we started at the coordinate point x is 1 and y is 1. So that's y is 1 here. And again, we're going up in 99 steps here. Okay, again, when you show that, if you follow this one through, you get 2 graphs. And then when you press Control T, oh, by the way, if you wanted to change your initial term and see what happened, I mean, that's what I did. It will change your red line completely. It will move it up, for example. But obviously, this is what we want in this question. So yeah, if you press Control T, it will give you the table, which is pretty beautiful. And then if you have a look down there for where x is 2, you'll find out the answer for y. Okay, guys. Sorry, it's a bit long, this video, but hopefully that's really clear. You need to have a go at this for all of these questions here. And you need to get some decent practice on this. It's a pretty difficult skill. Well done in getting through all of this. This is the end of Unit 11. So congratulations on that. In fact, it's the end of the teaching for the first year in HL AI Mathematics. So well done on that.